Welcome friends, we are into the 8th session of ARM web development. I hope you so far have been following the classes and enjoying that too, working on the lab. And in the last session we covered basic how constants are being managed for both logical and arithmetic data processing instructions. Okay, so that is for operand 2 of the logical or arithmetic data processing instruction. If you remember Rn, which was operand 1, anyway I will explain you with a diagram. So today in this session we are going to talk about logical instructions as well as arithmetic instructions, and how if we do operate on R15, that is program counter, how it is going to be impacted. Okay, this is a very interesting topic where you will understand the basic operations done by the processor, as well the freedom that you have to work on the PC register as any other general purpose register is very unique to ARM, but you need to be very careful with what to expect when you modify the values of R15. Okay, so today's session will be focusing on these two aspects. The first few will be on the logical and arithmetic processing instructions, and then we take an example of multi-word arithmetic. That is, you know that ARM supports only 32-bit data or registers, right? But there may be some scientific applications where you need to operate on 64-bit data, or it could be even 96-bit data. So if that is there any support from ARM so that you can even operate on data widths which are higher than 32 bits? So we will see some examples and the instructions which support them, and then the most interesting part will be how R15 could be used as a operands or as a destination register to achieve different things. Okay, good. So we are back again with the format. So if you remember, in the last class we spent whole session talking about how the operand 2 is, if it is given as a register and along with some shift operation, or an immediate value with some shift operation. So if any of these values are given as an operand 2, how does barrel shifter take that operand 2 and operate on the immediate value shift operation as well as some constant that you have passed on along with the instruction, how it takes them and then prepares the value for ALU. Okay, so again I am repeating, the operations performed on the using the barrel shifter is to prepare the operand 2 for the ALU. Okay, it is not the ALU operation itself, or to say. So to just clarify, suppose you have a left shift logical or rotate or anything, any operation you do on the barrel shifter is only to prepare the operand 2 for the ALU. Then what the ALU does is based on this opcode. The opcode is what? The instruction as such. It could be AND or move or compare or anything. So before doing this operation, the barrel shifter prepares the operand for it. So that is what we talked about in the yesterday in the last class. Okay, now let us see what are the different operations supported by the ALU. If the barrel shifter has done its job and then it has given the operand 2 here, and operand 1 anyway is always taken directly from the register file. So you cannot do any barrel shifter operation here. If you want to do it, suppose you want to have both the operands, you want to do some barrel shifting operation. Okay, barrel shifter means what I am saying is any logical operations you want to do on both the operands, then what you should do is you should perform that operation on Rn separately on the register and then keep that ready, and then you can work on the any logical operation that you want to perform on Rm and then give it to ALU. If you want to do it on both of them. If suppose you want to do it on only one of the operand, then you have to make sure that that operand is here so that in the same instruction it is done. Okay, I hope this is clear, and you know these values are, this is a destination register where the outcome of this has to go, and this any of course talks about Rn, and this operand could be just an immediate value, or it could be Rn followed with some shifting operation or logical operations on the barrel shifter, and then the operand is communicated. Now we are going to concentrate on various operations that the ALU supports, provided these operands are ready. Okay, after the respective functions are done. This is the set of operands available, the operations that ALU supports. Now a simple move, okay, this is very unique because it's a single operand instruction. Of all of them, if you see the parameters here, all of these other instructions have two operands to operate on, whereas except for this move which operates on only single operand. So these are the only unique single operand instructions. What does it do? It takes the value. So this single operand, is it Rn or Rm? Whenever single operand is there in an instruction, especially move and MVN, the operand is treated as operand 2, not operand 1. What is the reason? Operand 1 comes directly from register file, so you cannot perform any shifting or rotating operation with the help of barrel shifter, whereas operand 2 has the facility because that is the way the architecture is designed. So operand 2 goes to the barrel shifter before entering ALU. So when you have a single operand, the single operand is assumed to be coming from the operand 2 entry. Then what happens to operand 1? There is nothing. The move instruction doesn't even look for operand 1 at all. Okay. Now this is a generic way any instruction is defined. So you should be able to understand this, so that next time when I show you this, or when you see in any of the manuals, you get a clear idea. This part of it explains about what operation is requested by the instruction from the ALU. Okay, this is the opcode. Though the whole instruction is as a binary of an instruction itself is can be considered as opcode from the higher application perspective, but within assembly the opcode is only talks about the ALU operation. Then it will be followed by optional parameter. Okay, the flower brackets indicate that this may be there or may not be there in an instruction. Now by now you should all be familiar with this. This is a conditional mnemonic. It could be EQ or NE or AL. There are so many which on table I had shown you earlier, whether less than or equal to or whatever conditions, and this condition is based on the conditional flags. Okay, if this is provided, suppose MOV EQ if given, then if EQ condition is satisfied only this instruction will be executed, otherwise it will be considered as a no op. But it will go through the pipeline, and the execution stage it will not perform anything, and you won't feel the presence of this instruction in your register file or in the flags. Okay, this you understood. Now S is, again I have explained multiple times, this if bit is present, then the S bit in the instruction will be set, and which will indicate that this instruction is free to modify the flags based on the operation it performs, that those flags may be impacted. So it is not that when you put yes all the flags will be affected. It again depends on the instruction. Some instruction may affect only 1 or maybe 3, or it may not affect 1. I will show you where uniqueness of this happens, but otherwise this is indicates that this instruction when it is executed, if it is modifying any flag, any conditions, it will be reflected in the condition flag of the CPSR. Okay, and this is the destination register, and this is the operand 2 that we are talking about. So this can go through some barrel shifting operation before moving into RD. The value is moved into RD. That's all about move on, and you know that MV move just moves the operand to MVN, complements that does the not operation on it, and then moves the value to RD. Now this is a whole set of instructions are there. Please don't read this now. I will come to this point, this note later. Now let us talk about every instruction, what it does. And is very simple AND operation of by a Boolean operation. So these bits in operand 1 and operand 2 are ANDed with each other, and the result is written into. Okay. And again this has a condition, the this can be mentioned here, and operand 2 is AND with RN, and then the result is written into RD. So exclusive OR does an exclusive OR operation, and subtract, there is a operand 1 is subtracted from operand 2. It should be very clear which is getting subtracted from there. So always the convention is the first is considered after the destination register, the first is operand 1 and the second is operand 2. So subtract this value from this. Okay. Whereas reverse subtract does the reverse of this. Okay. That means it is subtracting this operand 2, sorry, it is subtracting the RN, the operand 1 from operand 2. You may wonder why there are 2 instructions required for this. If you remember the diagram earlier what I showed you, just we'll go back. I said only the operand 2 is going to the barrel shifter, right? Suppose you are interested in the operation, okay, here we'll come back. So here you want, in the reverse subtract, you want operand 1 to be going through the barrel shifter. Suppose you are interested in, sorry, if you want to subtract this from this, but this one you want it to go through the barrel shifter. So that is achievable in this RSB. You can write it this way, then it will take the operand 2. Flow is always same, but if you want to subtract the operand 2 from operand 1, this is becoming easier, right? This will always be the second value which you are subtracting, it is going through barrel shifter. Here the reverse is happening, right? It is on this side of the subtraction. So that is what the convenience given to the compiler and the assembly program. You can use anything, but you should be aware of what is getting subtracted from what. Okay. So add is simple addition. Now this is add with carry. What is the need for it? I will explain this when multiple I told you that there are additions possible where the operands could be more than 32-bit wide. Okay. So that kind of additions when you want to do, you perform 32-bit addition, and then that carry, if it is coming, you want to pass it on to the next set of values that you are going to perform arithmetic operation on. So for that the carry flag is passed on to this instruction. So this is a convenience. If you want to consider the carry also to be added with the operand 2, you will be able to use this instruction to perform. So I will show you an example here, and then you will understand that. Now subtract carry. Actually you are supposed to just subtract. When you are subtracting the operand 1 minus operand 2, the carry you wanted to subtract from. But here it is, what is written is carry minus 1. What does it mean? If suppose carry flag is set, you are not subtracting anything, but if carry flag is 0, you are actually subtracting 1. Why is it so? Actually your intent was to just subtract carry. The reason being, in the ARM processor, the carry flag is cleared by a subtract that needed a borrow. Okay. It is actually a reverse of what happens. If suppose there was a borrow, the carry flag is cleared when the subtract operation was performed. So in that case you have to do the reverse of what you would have done if carry flag was set when you needed when the subtract operation needed a borrow, right? So to comprehend this, what is being done, the SBC is implemented internally this way. But as a programmer, we don't have to worry about this. Okay. You can, as well as when you want to do a multi-word subtract, what you should do is you first subtract the lower words with yes. Why yes is required? Okay, you want that subtraction to affect the flags. Then only you can use that carry or a borrow flag carry and borrow flag are same. Okay, so the carry flag that you can use it for the next instruction. We are using a sub carry, subtract with the carry. This you will be doing it for the subsequent higher words that you are subtracting from. Okay, and why do you have to do a S here also? Because you want this instruction also to impact the flags, so that you can do the next higher word operation. So I have given you for example sub here, but you can do the same thing with the add also. Okay, you have to do add S here and then ADC S here if you want to do multi-word addition. So this is the way this is performed. Okay. Now reversal RSC is again just reverse similar to RSB. RSC is with the carry also you do, but operand 2 comes here and operand 1 comes here. Okay, and then these two are all Boolean operations. OR operation, this is just it performs an OR operation between 1 and 2, and this what does it do? It does the complement of this and then adds it to the operand 1. So I will tell you what is the need for this. Okay, this is to clear off some bits. Okay, in a particular positions we want to clear some bits. You need to whatever bits you want to do clear. Initially that you will be mentioning it here, and then you do a NOT. Then those bits will become 0, and when you add it with them, the operand 1, those relevant bits will become 0 here. So you are effectively clearing those specific bit position by mentioning them in the operand 2. So this does this job. I hope you are clear with this set of instructions. I will show you some examples in the subsequent slides. Now, what are they? This is actually this note is not relevant for this instruction. Okay, please ignore this. When any of this test is done, what does it do? It actually does the AND operation with the both the operands, operand 1 and operand 2, and based on the result, it will impact the flags. But the result will not be written into any destination register. So you won't be mentioning anything here. It only takes two operands. There are no. You need to mention only two operands which need to be tested against each other, and you won't be mentioning any RD, the destination register. So what does it mean? Test means it is actually comparing two values and sees whether they are same or not. Because when you AND it with the the same bits, if they are set, you will get the same value again. Okay, so based on that, it will set the flags, and you will know that they are equal. The values are same. The bits are same. Test equal. What does it do? This actually does the XOR of that, and then it compares whether the particular bits are all become 0, because when you XOR the same value with the same other two sets value, then you will get the 0 here. So if you are getting 0 flags set, that means they are equal. Okay, so that is the job. So it's comparing two things. That actually it performs a subtraction and then flags are impacted. And CMN is actually it performs an add operation and then impacts the flag. So basically these instructions are provided where you want to look at the flag, but you don't want to really perform you are not interested in the outcome of these values. Okay, only the flags you want, but not the actual result coming out of this instruction. Then you will use this. Okay, this is about compare and test. Tests are called on the Boolean operation, as well as compare is performing the arithmetic operation. Okay. Okay, let us see some examples that will make the things clear. The data processing operations may be classified as logical or arithmetic. The logical operations are all of them. Okay, even the TEQ and the test are logical operations. Understand that? Okay. So it is working on the bit level. Okay, it is not trying to understand the values of those bits. It just does a Boolean arithmetic or Boolean operations like OR, XOR, or AND, and then affects the carry flags if it is other flags. Now, when you perform a Boolean or logical operations, always the overflow flag is unaffected. Why? Overflow is useful only when you are doing a signed operation, right? So when you are doing a Boolean operation, there is no interpretation of signed or unsigned here, right? So because of that, overflow flag will not be affected even if you have a S bit set in any of these instructions. Okay. Now RD is not R5 is a special condition. We will have another last session we will be talking about that, so let us not worry about that. Now carry flag, of course this will be affected based on the, if suppose you perform any shift left or rotate left or logical or arithmetic shift, the last bit coming out will be impacting the carry flag. Okay. And if it was LSL 0, I talked about this in the last section. It will preserve the carry flag of the previous value, whatever was the previous value. Okay. And 0 flag will be set if the result what you get in the end of the operation, if it happens to be 0, you will get a 0 flag set. Okay. So only this N flag will be when bit 31 is set. So only these 3 flags will be affected by the logical operation, but not V flag. So these you should remember, and you should also know the reason for that. Okay. Now let us see. Take some time, just freeze for some time if you want more time. Find out what is the right answer for this. Why is V flag unaffected by the logical data processing instruction? It could be since V flag and C flag are always the same of any logical operation, or because it will delay the execution of logical operation, or V flag is valid only when the arithmetic operation is performed. I think in my discussion I have already told the answer. So this is C. Okay. So V flag plays no role when logical operations are performed. You should remember in this. Okay. Now I told you that compare and TEQ, there are 2 instructions. What do they do? And why are they? Why there are 2 instructions? Both doing the checking whether operand 1 and operand 2 are the same or not. Okay. Then what is the difference? Why is given us 2 instructions for this? Both do not write the result. Okay. You know that compare and TEQ both will not write the result because RD is not mentioned. So I am telling you both are equal in these 2 aspects. Now we will see where is the difference coming. There is a minor difference in their behavior. Compare affects all the flags. Why? It does a subtract operation internally, right? And then the result is not returned, but it performs a subtract operation. Operand 1 is subtracted from operand 1 minus operand 2 it does. Okay, that is better to say. So operand 1 minus operand 2. So and you know any arithmetic operation will affect all the 4 flags. So compare does that. So it will affect all the 4. Again you should remember, irrespective of whether S is mentioned or not, actually compare always affects the flags. It is not based on S. That is one important thing about compare and test. These instructions, even CMN as well as the other test ES, other instructions, the 4 instructions which do the comparison job, they always affect the flags, irrespective of whether S is mentioned or not. Some compilers, some assemblers may crib if you may give warning or error if you put S. Some may accept it, but internally they set the S. Okay, those are the flags are set. That's one important point I missed out in the last slide. So TEQ affects all the flags except V flag. So that is the difference you see. Suppose then why there are 2 instructions? Use TEQ when you need to preserve the state of V flag while performing equality check. Suppose you want to perform an equality check, you have an option to choose one of these instructions. Then if you are dependent on the previous value of V flag, then you better use TEQ, because if you do the compare, that may be overwritten by this operation. So if you want this to be preserved, perform TEQ so that you can use that in a subsequent instruction. How do you use it? Maybe you will put less than or greater than signed values. You can compare, and then based on that you can choose to execute an instruction or not. So if you are using V flag, remember to use TEQ before that if it is needed, if you want to do a comparison job. Okay, so that's all about logical operations. Now let us talk about arithmetic, these are the things. Why this compare and compare n is also listed under this? Because they are internally performing the subtract operation, which I told you. So they also fall under this category. They operate on 32-bit integer, of course, because that's a bit of our registers. Now, one thing I have mentioned earlier, but I am just stressing on this point. Only the programmer or the compiler. So why compiler? Because if suppose you have declared an unsigned int u, the name of the variable is u, and then signed int yes, you have declared two variables with one being unsigned and another being signed, and then you do a addition or subtraction, and then you are comparing whether this one is more or less. You are comparing unsigned values or signed values. While writing the program, you might have mentioned the variables to be unsigned or signed. Then compiler knows that okay, this variable is signed or the other one is unsigned, and then it will accordingly choose which flag to look for when it has to do a comparison. Okay. As far as the processor is concerned, what is stored in a register is an integer, of course, 32-bit integer, but it doesn't know whether it is holding a signed value or unsigned value. So the processor, when it is performing any arithmetic operation, it will impact both the flags based on how you are going to interpret. So it doesn't know that whether what you have really put inside the register is an unsigned integer, because the representation is how you interpret the value is different in case of unsigned or signed. So any arithmetic operation will impact both the flags, and you are free to choose one of them based on what you know about those variables. Okay, so this is very important point. Remember that. Now again, I told you that any of the arithmetic operations also can be followed with appended with a yes or no. If there is an yes, then the assembler, when it is generating the binary of output for this, it will put that S bit set inside the instruction. So then processor will know that okay, when I am doing this, I need to impact the flags. Okay. So if S bit is set only, we will be talking about this flag. Otherwise, in none of these instructions change the values of the flags, conditional flags. So B flag will be set only when the overflow occurs if the values interpreted were 2's complement value. One more thing you need to remember that internally ARM processor, I think most of the processors in the market, negative numbers are represented as 2's complement and they are treated like 2's complement. The arithmetic what it does is a 2's complement. If it is a negative value, it's a 2's complement form. Okay. If suppose if you are maintaining 1's complement and then you are trying to put that value into it, if your interpretation is 1's complement and actually processor is 2's complement, then you will have a different values. So you should remember that most of the processors, almost I think in the market, everything treats the negative values as 2's complement. So when you are treating the signed integers, you need to treat it as a 2's complement value. If it is negative, you have to, if MSB is set, you will complement all the bits and add 1 to it to find out the magnitude of the negative value. Okay, C flag is set if it's very simple. If bit 31 is set, the C flag is set. So these are all the results which are coming out of the instruction. Okay, not the operands. This is after the operation is performed, what is the result, and based on those conditions, these flags will be set, provided yes is there. And N flag is set if MSB is set. So you may interpret it based on the N flag. If you have to as a 2's complement, then it shows the negative value. Okay, that's it. So this is all about how arithmetic operations impact the flag. Let us see some more details of it. Add instruction adds the value on Rn with the operand 2, and Rm, that is the operand 2, if it could be a register coming from Rm, or it could be immediate 12-bit. Why I put 12 here? That you know that the immediate constant value, whatever is the space provided for the instruction by the instruction is only 12 bits of constant, or combination of both. Suppose you are doing a shift operation, then you will have a constant associated with the Rm, will be a operand 2. Okay. The subtract instruction does the same thing. Only thing is it does operand 1 minus operand 2. So operand 2 is again coming from any of these. Now reverse subtract, is operand 2 minus operand 1. Okay, this is useful because barrel shifter has more operations for operand 2. Okay, that's why if you want to do a operand 2 minus operand 1, and but you want to do more barrel shifter operations on the operand 2 here, then you will be able to perform this using this instruction reverse subtract. So you can do along with the carry. If you want to do a multivariate arithmetic, you can use any of these instructions. This will be covered. Okay, an example for this multivariate arithmetic will be covered soon. Okay, within a few seconds or minutes. Now this is what add C is. Instruction adds the value of operand and operand 2. Okay, together with the carry flag. So if carry flag is set, then one more will be added to this value. If it is 0, it is same as add. There is no difference. If there is no carry flag, if carry flag is 0, the addition of operand plus operand 2 will be same as what you would have got with the add. But if carry flag is set, it will be one more than what you got with the add. Now subtract with carry, it is the same impact. The carry flag borrow is there, then it would have done it. But internally, because carry flag is clear because of borrow is there, the carry flag is clear, the result is reduced by 1. Okay, it's a reverse because of the implementation I mentioned earlier, and that is true with RSC, reverse subtract with carry. And one more thing, just wanted to caution you that the assembler may substitute some different value, different instructions. So when you are reading the disassembly listing of the instruction, you may have to, and more than assembler, the compiler may do the same. Okay, you may expect some instruction to be there, but it may have something different because it would have optimized something. So when you try to understand the assembly listing of what you have got from the compiler output, you may have to think about what are the changes it has done. Maybe there may be some dependency on the previous instructions also. You may have to read the complete flow to understand if there are any differences in the instruction being used by the compiler. Okay, very good. Now let us see a multi-word arithmetic. So simple addition, all of us are aware. So just wanted to give you an example of a multi-word arithmetic. That is, suppose you want to perform a 64-bit integer addition. So first of all, how will you store a 64-bit values when you have the registers which are only 32-bit wide? You will split the 64 bit value into 2. The LS part of the word, the least significant word, can be stored in one register. So in our example, we have stored like this. Okay. So we have two sets of registers. One is stored here, and another one is stored in this registers, and you are subtracting it. Now, here you are adding it. Now, when you are adding it, what is happening is first R0 and R2. Okay, you remember the format of instructions. This is RD, destination register. This is operand 1, and this is operand 2. So this is operand 1, this is operand 2, and it is subtracted. Added. Operand 1 is added to operand 2, and result is written into R4. Now, why is this S is given? It is very important. You have to give S because you are based on this addition. If you do this R0 plus R2, there may be a carry from the result, which should also be added with this to get a correct value. Otherwise, you will get a two additions, but it will not be correct. It's simple as when you have 12 plus 19, if you do 9 plus 2, if you add, after that one carry has to be added with this. Simple our school days we have studied about the addition. So that is true with the multi-word arithmetic also. So when you are adding this, these are single 64-bit words. So when you add these two, anything coming out carry has to be given to these values to get the final result which is correct. So you need to use add C. Add with the carry you have to use, and very important that you have to put yes. If you miss out on this yet, whatever is the previous value of carry flag will be taken by this instruction. So you may get a correct result sometime, and you may get something wrong at some other time, because it purely depends on what was the state of carry flag before it came here. So these two are adjacent instructions, and you should not put any other instruction in between which affects the flag. and you should perform this one after the other and make sure that S is there. Now add with carry also, you are free to put yes or not, but I have put yes here because any result will be valid only if suppose even this also overflows, and you need to look at the carry flag to see that the 64-bit addition is either overflown or not. But it is not mandatory. If you know that I am not going to exceed the limit of 64, yeah, you need to do it, but it is always better to make it a habit to do this, because it is not going to add any delay or anything to your execution of the instruction. It is only later on you can decide to use those flags, conditional flags, based on the requirement. So this is a safe way of programming in assembly. Now I want you to just hold on, pause the presentation, and then try to map these instructions into a 96-bit operands. Okay, what I showed you is 64-bit. This is 32 and this is 32, so adds up to 64. Suppose I have a multiword, I want to perform a 96-bit operation. Here I am interested in subtract. Okay, now how do you map these registers? You see a lot of registers here. How do you map them into this? These 9 registers have to sit into one more column you have to add, and then you have to map them. I want you to map these two values and the result value also, so that when you are writing this multi-word arithmetic, you are clear about how to mention the operands. If you modify, change the sequence, you will get different results. I hope you have already tried it out. Let me show you. Hope what you have tried and what you are seeing is correct. See here, this is whenever you are doing any arithmetic, as in the school days we have learned, you have to perform the arithmetic from this end, right to left. So you have to perform the operation on the lower significant words. So that is what is given as a parameter. So which is operand 1? We know based on the ARM's instructions format. Operand 1 is this, that is why R6 is here. Subtract it from operand 2. Sorry, always mention it wrongly. So R9 is subtracted from R6. That is operand 2 is subtracted from operand 1. So R6 minus R9. So you have to be careful. And where the R3 goes, I am not shown here. Where does it go? It is a result. So let me show. R3 comes here. Now R7 minus R10 and the result R4 sits here. R8 minus R11 and the result goes to R5. Okay. One more, and of course the instructions need to be careful. You cannot put sub here. You have to put sub C, SBC along with carry, and here also SBC, and S here is a must. Okay, if you don't do it, then any carry coming borrow from here will not be reflected for the when you are doing a third set of operations. So this S is a must and this is optional. If you want, after the result is found, you are interested in what has happened to the result, you can put yes, but these two are important. Okay, so take some sample values of this and then put them in registers and then see the result. Okay, now another thing what you notice here is these registers are all sequential, right? R6, R7, R8, R9, R11. Is it required? Is that we need to be very sure that when you are doing the operand, R6 should be here and then the next higher register should be there? Actually not. You can use any registers you want, provided you don't overwrite on them. Then results nobody can predict. But as long as you are not overwriting any of these values and you are careful when you are overwriting also, okay, then you will be able to see the proper value. Here you see R9 is there in two places. Will it impact? See here, operand 1, operand 2, this is operand 1, this is operand 2. It is performing the subtraction here and the flags are already affected. Now this result I want to write it in R6, that is fine. Now R2 and R1 is subtracted and the result is written into R9. Now what happens? This is actually overwriting on one of the operands, but it is okay because this operation is already performed. So you are not you don't need this value anymore. So you are free to modify it, but you have to be careful when you are reusing any of the registers. But okay, and then R8 and R11 is written into R2. Now you see here these values or registers are all arbitrary. There is no any inherent sequence as it was in the earlier example. So why I mention this is you should remember that the ARM processor or typically any of these operations are performed here. It doesn't take any sequence between this, whether you are ordering them in a particular sequence or not. It just does what you are given here. Okay, so as long as you don't overwrite which is required for the next addition or subtraction, you are free to use any registers you want. They treat them as a two operands to the operation, that's all. But please remember that S is a must in these two cases, of course. Okay, I hope you have understood the multivariate arithmetic here. I want you to do this with some different values, both positive and negative, signed and unsigned, and then see the results for you to be sure about this. Okay. Now it's an interesting part of the discussion, R15. Why R15 is so unique? Because this is a program counter, because this is pointing to the instruction being executed. But the freedom that we have with ARM is this is also part of the register file, though it has got separate read and write ports to enhance the performance. It can be treated as any other operands to any other data processing instructions. But you have to be careful about what you are doing with this, otherwise you will get an unpredictable result. So you have to have a clear idea when you are using R15 in your instruction. You should have a clear idea of what to expect, and unless you understand the pipeline and how internally the values are the PC are modified, you will not be able to use it efficiently and correctly. So please pay attention to this. Adding any two register values and a constant, you could use PC for Rn. Okay, this is allowed. If you use PC as Rn or Rm, okay, you can use Rn and Rm also. We have shown only these examples I have given. You can have RD also. I'll tell you how to be careful about what you need to be careful about. Now suppose you are using it as Rn and Rm. What is the difference between this? Rn is the operand which is coming straight from the register file, and Rm is through the barrel shifter. So it treats R15 as a generic any other register, so it can read from the instruction can read from the register file. But I am saying the value is current instruction plus 8. This I have touched upon this when I talked about pipeline. If you remember, there are three stages in the pipeline in ARM7, and first is fetch. Okay, maybe I will draw. Okay, fetch. Next stage is decode, and third stage is execute. Now you have to remember, when is the operands for the operation whatever you are performing is read from register file. If you remember correctly, it is done at the execute stage. Okay, whereas in ARM7 it is done in a decode stage, ARM9 in a 5-stage pipeline. But here let us restrict to ARM7 now, and then there are 3 stages, and operands are read during this execute stage. So if R15 happens to be one of the operands, where is the R15 pointing when a particular instruction is in this stage? You remember, before this instruction comes here, the next instruction is already inside the pipeline, which is in decode stage, and next to that whatever instruction is there, that is already fetched and it is in the fetch stage. Now where does R15 point to? When you have instruction 1, instruction 2, and then instruction 3, suppose 3 instructions are there, you are executing an operation here, add, okay, and then you are using the R15 as operand here, okay, maybe Rn or Rm, to write it into Rd. When are you reading our PC? Okay, this is PC. When are you reading this PC? When you are in the execute stage of this instruction. But by the time R15 is pointing at this 2 instruction down the line. So each instruction, you know that it is occupies 4 bytes each, right? 4 bytes, not bits. Okay, let me write B. So it has already advanced by, if suppose this was 1000, 1004, 1008. So plus 8 it has gone. That is why when during the execute stage, when in this instruction is interested in reading the operand, and if this operand happens to be R15, it will not get its own address where it is residing. It will get the 4 bytes, 8 bytes, and always it is in the increasing order. Always PC is incremented, so it will be 4 bytes more than 8 bytes more than the current instruction. Remember, 8 bytes more than the current instruction. Okay. So if you are performing any operation on and taking the R15 as an operand, you have to remember this. This actually, it should take you to even the pipeline. You should remember the pipeline. What is exactly happening? You should not just mug up that, oh, okay, whenever I am using R15, I should have 8 here. Now whatever I am getting is plus 8. No, it is because of this reason. Please remember that. Because this pipeline, these are the pipeline stages I have gone. Okay. Because of this, and the operand is being read only in this stage, you will get a value which is 8 bytes more than the address of the current instruction. Okay. I hope this is very clear to you all. Okay. Let us see few examples so that it's clear to you. If you are using a PC as a RD, okay, what suppose RD is what? The destination register. The execution branches to the address corresponding to the result. It is true, right? When after any arithmetic operation or a move operation, you have changed the value of R15 because you are using that as a destination register. That means whatever you are writing, you want that to say to the processor that I am writing a new address to you. Please pick the instructions from there. So it is supposed to do that. So whenever RD is modified, it will start executing the instruction which is stored in that address. Suppose if you use S flag suffix is a separate interpretation for that. I will talk about it later when it is appropriate. So just for a moment you ignore this. You can use SP also for Rn. What is SP? The R13. Okay, remember R13 is another special treatment is treated as a stack pointer. So you can also use SP. There is no there is no restriction. Okay, so I hope you understood this. So let us see few examples for you to understand this. Now assume that R0 is holding a 1000 value, 0x1000. Okay, this hexadecimal value. R1 is having 04. Now I am interested in performing this operation. I am interested in loading the R15 with the new value. So what happens? R0 is 1000, so it just simply adds 4 to that and then writes into it. Now remember that you need to be careful in whenever you are changing the value of R15. Here it is a ARM processor, ARM mode, so we are not talked about thumb mode at all. So let us, in this ARM mode, the lower 2 bits of the addresses stored in R15 are zeros because it's always 4 byte aligned instruction it is going to fetch. So you have to make sure that you don't change those convention, okay, because different processors may implement in a different way and then you may get a different results and side effects. So you have to make sure that the resultant value what you get should not have the LSB 2 bits, the lower 2 bits, bit 0 and bit 1 should not be set, it should be zeros. Then in the ARM mode, okay, I am very particular about that. In the ARM mode you have to take care of that. Thumb mode is totally different, which we will talk about it when I talk about when we touch upon the sum mode in execution. So here what I am trying to say is you should not add 2 or 3 to it. Okay, R1, R1 1 you are 1001 if you write into it. Some processors may ignore the 2 bits and then access it from 1004 or 1000 only, but it's not good programming practice warrants that you don't do this. Okay, that's why I'm telling you that whenever you are changing R15, it is not like any other register. It's something to do with the program counter. So you will immediately see if you are running this code in your simulator, you can immediately see that the execution jumps to the address what it is pointing at. Okay, so the difference between this and this is an S is added, of course. Then you will see that the flags are affected. Why all 4 flags are affected? Because you are doing an add operation, of course, and then the result is same. It actually moves to 1004 only both cases, but the only thing is the flags are also impacted because of this instruction. Now another example. Suppose this is very I have complicated a little bit. I am reading from R15, okay, and then adding it to R2 and writing into R15. So here we are doing a subtract operation. So R15 is taken. Okay, when this instruction is executed, when it is in execute stage, the value of R15 at that moment is taken as one operand, which is directly taken as Rm, and then Rm is just R2, which happens to be 8 here. So you are taking R2, and now R15 is subtracted, R15 minus R2, and then the result is written into R15 again. So PC value is taken and subtracted from whatever the value of R2 and then written back. Now what do you expect here? If you remember, just now I mentioned that what you see in R15 is not the address of this instruction, it is plus 8. Okay, so because it has R15 has already advanced because of the pipeline prefetching, it is now trying to prefetch 8 bytes ahead. So effectively what are you trying to do here? From this address, wherever it is now 8 bytes plus 8 bytes it is, you are subtracting minus 8 from there. So effectively you are bringing back the value of R15 into the same instruction. So I urge you to write this code. You make sure that you don't have to do this precondition because already R15 anyway is there. Only R2 you make sure is move R2 comma 0x028 you do, and then perform this and see what happens. You will see that the simulator will not move from this instruction because every time when it executes this instruction, it is bringing the R15 back to its own instruction. So the pipeline will be flushed again, it will be loaded with the same instruction, and then it results in the same value. Because what are you trying to do? Whenever R15 is going ahead, you are bringing it back to this location. Again it goes back and again, so you will be continuously in this loop. So this is a very good example to try it out. Is try this and understand it, why it is happening. What I explained in the previous slide is the reason for it. Okay, so because operands are read during the execute phase, the R15 has already advanced by 8 bytes. I am again summarizing it. So R15 has already advanced by 8 bytes because it has already fetched 2 instructions. One is in decode stage and another new one what you see this fetching is in fetch mode stage. At that moment you are taking the value of R15, taking a snapshot of that value and trying to subtract the value by R2. When you subtract R2, this R2 happens to be 8, so you are bringing the value back to the address of this instruction. So it will come back to this and then it will continuously be in infinite loop. Okay, I hope this is very clear to you. Now one more example. Instead of doing it from R2, you could do also from the immediate value. Both have the same effect. Only thing is it is coming as an immediate constant. Okay, again subtraction. What happens if you do addition here? It is here. It will go to another 2 bytes ahead. So you will jump 4 instructions and then start executing it further. So I urge you to try different things, but the only thing is you have to have valid instructions. Maybe what you can do is write your assembly code with lots of move instructions, maybe 10 15 move instructions to R1 R2 R3. You move different values into R1 R2 R3, maybe to have a clear idea. R0 you move it to the R0 1 2 3 4 like that, and then try to in between you squeeze in this instruction and you change instead of subtract add it, or instead of 8 you do some other addition, but please make sure that it is always divisible by 4, this constant, and it should not be more than 12 bits, because you remember the immediate constant cannot be more than 12 bits. If you do that, you will be able to see the where does R15 go, and if it crashes, that means you have updated with the wrong value. So debugging will be very difficult when you are modifying R15 value, so you need to be very careful about it. Okay, another example I will show you. R13, you know that it's a stack pointer. It's already with 1000, sorry, 0x1000, and then we are adding it 4. So it is same. No, R13 is also treated the same way. No difference. Okay, and you could add it with a constant also. You will get the same result. You know, it will jump to 1004. It's a constant jump. So 0x1004, whatever instruction is there, it will start executing from there. And what does it do here? I am just showing you that you could also have a barrel shifter operation, some logical shift right with whatever is the content of R3. You do this, you will get again 8 bytes. Okay, I want you to try out all these instructions and see yourself what happens. Now one question. Okay, when R15 is used as one of the operands, as I showed you in the previous examples, can its value be more than +8 compared to the address of the executing multi-cycle instruction? What I mean by multi-cycle instruction, it could be load or store multiple bytes, okay, or it could be a mul instruction, okay, or add in any instruction with executes for more time. Actually, even it could be a RS. If you are using RS as a register for shifting operation, okay. Assume that an instruction which takes more cycles, because suppose if you are doing multiple store, you will be having a different memory cycles, okay. So the execution stage is not completed in one cycle, it could take more than one cycle. If that is the case, can R15 be more than +8 than the current address? Think for a while. What happens in ARM7 TDMI with the 3-stage pipeline? If a particular instruction takes more cycles to execute, what happens? Will R15 go further? See, start with any instruction needs to cross 2 stages to come to execute stage. So 2 cycles are already done. So it is incremented by 8. Now what I am asking is, in the execute stage, if that instruction takes more cycles because it is a multiple store, so there will be more store memory cycles will be involved in storing or loading the values from the memory. During that time, can R15 go beyond 8 bytes and keep on accessing instructions down the line? Think for a while. Okay. No. Okay. Now I told that it is no. So can you reason it out after hearing this? If suppose you thought it is yes. So let us see. This quiz is about. I'm sorry, the answers are okay. Options are there. Okay, this quiz is about the reason for that. I said that okay, it can't be more than 8, but why? Let us see one by one. Operands for the instructions are read from register file earlier than execute stage of the pipeline. I am not making any, whether I am not saying that whether it is true or not. It is because I am saying it can't go beyond 8 because the operands are read, the R15 is read earlier than the execute stage. Okay, so it can't change even if multi-cycle instruction is executed. whatever you are read from the register file stays same, right? It cannot be more. It can't keep on changing based on the multi-cycle instruction. Even if multi-cycle instruction is being executed, pipeline is stalled until the current instruction is completed, because of which the instruction prefetch cannot happen not more than 2 instructions ahead. What I am saying is, even if this instruction, particularly execute stage, whatever instruction is there, it takes multiple cycles to complete. Can R15 proceed further? It can't, because unless this instruction goes out of execute stage, the decode stage instruction cannot move into execute stage, and the fetch cannot move to decode, and the new instruction cannot come in. So what I am saying is the pipeline will be stalled if any one instruction takes more cycles. So that is one reason. Another one is, even if R15 is added by more than 8 bytes, its old value is maintained in temporary location. I am saying that the other option says that R15 is stored in a temporary location somewhere. So because of which the old value is maintained, that +8 is there, so it can't be more than +8. So again read this question as well as answers, and then come to a consensus which one is correct. Okay, it may be equally confusing, all of them, or you may be clear about the option to choose. Okay, the correct option is B, because there are more explanation for this, so that should be the reason. If you are thought because more lines are there, that option should be correct, please don't do this. Next question I may have totally different combinations. So the reason being, the pipeline is stalled when a particular instruction in execute stage takes more cycles to complete. The good example will be multiple store or multiple write, read, load or multiple store or load. The R15 also stops because we can't fetch any more instructions, because decode stage also freezes, fetch stage also freezes until this execute stage, whatever instruction is executed is completed. So R15 cannot go beyond 8 bytes. I am talking about ARM70 DMA, not for the future processors. There may be some processors implementation will be different. So this particular discussion is only for this. Okay. Okay. Now let us talk about the incremental cycle times of each instruction. Okay. The normal data processing, one sequential cycle. Why is it one sequential cycle? I told you that pipeline as start, instruction keep coming in, then the effective throughput will be one instruction per cycle. If there are no stalls or if there are no flush, then you will see that every one sequential cycle, one instruction will be coming out of the pipeline. So effectively any data processing instruction will normally take 1 S. S is sequential cycle, N is non-sequential, and I, this is I, which is internal cycle. If you remember, I have explained about these cycles earlier. Sequential cycle is, if the instructions are accessed from the sequential addresses, it will involve some time which is equivalent to sequential cycle, because memory is provided with the subsequent sequential addresses. Non-sequential addresses, because it is provided with a totally new address, it has to fetch from a different location, and there might be some delay involved based on the type of memory that you are interfacing with the processor. So N is non-sequential address is how much time it takes, and internal cycle is something the processor wants to do internally, some operation which doesn't involve any memory access. So that is internal. Now let us see. Before we see the reasons, I want you to even think about it. Why these are the timings given for different instructions, so that you have a clear idea. Now let us see what is the reason for a data processing with a register shift specified shift. What I mean by register specified shift, the shift value is not immediate constant. It is stored in the lower 8 bits of a register. If you remember RS. Okay. Now when the register is holding the shift operation, what constants, how many shift operations need to be performed or rotate needs to be performed. If it is held in the RS, there is one cycle involved in first reading that register and then performing that operation, okay, on the RM, and then feeding both RN and RM to the ALU. So internally there will be one more cycle spent if there is a register specific shift in the instruction. That means for the operand 2, if I had mentioned my shift constant is in the RS, that means if I put add R1 comma R2 comma on R2 comma R3, that is the second operand, you are saying that LHL RS, that is RS maybe some R5 or something. So if you are doing a shifting operation based on the content of the register, another register, then it will involve one more cycle. Okay. Now, if suppose a data processing is on PC, that means RD is a PC. What happened? This instruction has changed the value of PC. Once the PC value is changed, a non-sequential cycle is started because it is not same as the sequence that the current instruction is going. So there will be a one non-sequential cycle because it has to fetch a new instruction and flush the pipeline and fetch a new instruction by performing a non-sequential cycle with the memory and get it into the pipeline. Now where does it get that instruction? It cannot directly get it into execute stage. It has to get it into the fetch stage. Then one more cycle, two more cycles will be elapsed, the fetch stage, and then it will take one more cycle for that instruction to come to decode stage. Then only it will come to execute stage. So the next instruction, which is fetched based on the PC value, new PC value return, will experience a delay of 2 sequential cycles. See, again this particular reason is because of the pipelining. I am not blaming the pipelining because you are getting so much of performance in a normal flow of sequence, but when you are changing the flow, when you are flushing the pipeline, anyway we have to live with the delay involved. So any performance, no pain without no gain without pain, right? So you have to live with this 2s delay because you are changing the instruction from where you have to fetch the next instruction. It is not the next sequential instruction. So you have to flush the pipeline, which has already the 2 instructions which are coming to the pipeline have to be flushed, and the new instruction has to be fetched. So that is the reason. Now this is, you are doing a register shift operation also to find the value, new value of PC you are trying to find, but you are doing some register shift operation along with that. That means you will have one more internal cycle because of the register shift, always there is one internal cycle, so that is also added to it. So it's a combination of the second and third. Okay, I hope this is clear to you. Now before we end the session, some examples. I want you to by now you must be familiar with all the instructions. Whenever you see an instruction, you should be able to, it should come on your mind, okay, what is happening here. You should not be reading the, nobody will be there to write the comments because you are supposed to write the comments when you are writing assembly code. So whenever the familiar assembly instructions you see, you should get in your mind that what is happening. That is very important to get familiarized with the reading assembly instructions. So I urge you to read lot of instructions and see what is happening there. Now spend some time in understanding each instruction. There is no sequence, it's all independent instructions, but are given here to see your understanding. So add EQ does it. If that flag is set, please remember EQ is there, 0 flag is set, then this is added and put into R2. Please, you should have by now you should have got this. What is TQS does? It tests R4 equality with 3, and the S is in fact redundant as the assembler inserts it automatically. What I mean by that is, even as a programmer you have mentioned yes, or if you don't mention yes also, anyway it is going to impact the conditional flags because all CM compare instruction and test instructions affect the conditional flags. So S is redundant here. So lengthy, but you should be familiar now after having listened to the last section. See here, register specified shift is given. Whatever is the lower byte of R2 is taken, that much of logical shift right is performed on R7. So it is very easy. LSR takes the offset value instead of hash 0x and constant. It is taking from R2, and you should remember that it is the lower byte of R2, and then that many times it is going to do this operation on R7. So now operand 2 is prepared. That operand 2 is done something with R5 based on this instruction. So R5 is subtracted, R5 minus this value is written into R4. Okay. Now what does this do? This does just R14 is moved into PC. So this basically normally when you are calling we are not covered that. So that's why it may not be familiar to you, but R14 is a link register. We will talk about it later. But actually at this moment you can think that whatever R14 is pointing at, it will start executing from that location. Okay. Now what is the difference between these two? The only thing is this doesn't impact the flags and this impacts it. That's it. Apart from that, there is one uniqueness about this. Okay. It will be clear to you when I talk about modes. Let me explain here. This is very specific because I told you earlier that I will explain this in section. Normally when there is a mode change or exception has happened, the previous value, suppose one instruction has caused an exception, then the address of the next instruction which is supposed to be executed will be stored in R4. This is linked automatically, and at that time even the flags are also copied into the new SPSR register. This is a stored program status register, okay, of the new mode. So when this is executed from the new mode, it is copying both the new value of PC from R14 and then the old CPSR which was stored in SPSR is also restored back. For this moment, if you don't understand, don't fret. I will talk about it when we have a discussion on mode changes and how exceptions are handled. During that time this will become clear, but you have to remember that this is a specific special instruction which does something more. Okay, so that's enough for now. So with this we are completing the session 8. We have touched upon logical data processing instruction, then all the arithmetic data processing instructions, and what are the flags get affected by each of them, and how to perform multi-word arithmetic, and then we talked about how PC could be used in the data processing. We saw few examples too. So this is the right time where you have more instructions in your hand. That means you are familiar with more instructions and more different ways of writing them. So this is the time for getting into a serious assembly programming, and we will be given with lots of lab assignments, and you will be able to enjoy these sessions in the lab. Okay, I hope this session was useful, and thank you very much for your attention, and hope to see you in the next session. Have a nice day. Thank you.